Good morning, everyone. So, welcome to my YouTube channel, Math Satram. So, today we are 12th lecture on Riemann integration. So, let's start today's session now. Note, let f close interval a b to r be a bounded function, and there exists k and capital K belongs to R such that so let's say it's small k1 and k2. Okay. Here exists small k1 and small k2 belongs to R such that k1 less than equal to fx less than equal to k2 for all x belongs to closed interval a b. Then if uh, if f belongs to R a b, then k1 b minus a less than equal to integral a b fx dx less than equal to k2 b minus a. Okay. So let's see its proof. Let p is equal to a x naught x1 x2 x1 is equal to b b a partition of closed interval a b. Then because k1 this happens, okay. So this is happening. What does it mean for all x belongs to closed interval a b? So what does it mean? It means small k1 is less than mi, mi is less than capital Mi, and capital Mi is less than k2 for all I goes to 1 to n. Now multiplying both this side by, so this implies k1 delta xi less than mi delta xi, mi delta xi k2 delta xi for I goes 1 to n. Now taking summation. So k1 will come out delta xi Now, what is this? This is B minus A. This is B minus A. A1, B minus A, L, P, F, U, P, F. A2, B minus A. For any partition P of closed interval A. Okay. Now, letting because function is Riemann integrable, letting norm P tending to 0, we get what we get when norm tending to 0, LP will tend to Riemann integral of F. UP will also tend. So this implies A1 B minus A is less than A to B Fx dx, that is less than A to B minus A. So this result is proved now. Okay. This is proved. Now remark, let F closed interval A B to R be a bounded function and there exists k greater than 0 such that k greater than equal to 0. K can be 0 also, we do not know, such that mod x is less than k for all x belongs to closed interval A B. If F belongs to R A B, then mode of integration A to B Fx dx is always less than k times B minus A. Okay. So let's prove it. So Fx satisfy this for all x belongs to closed interval A B. So this implies, what does it mean? It means minus k less than equal to Fx, and this is less than k for all x belongs to closed interval A B. Now what is k1 here? K1 is minus k. Okay. If F belongs to R A B, it means F is Riemann integral. Then by remark, then by norm, we have minus A B minus A is A to B Fx dx less than k times b minus c. Now, what does it mean? How we can write it? So, what is the meaning of this? We can write this a to b fx dx less than k times b minus c. Okay. So, this is true. Okay. So, you always remember one thing. Okay, one thing. So, you remember this. This. Remember. Remember this. A is sorry. Alpha is, always remember this inequality. Mod of alpha is less than mod beta if and only if minus beta less than alpha less than equal to and beta. You take any two real numbers alpha and beta. If mod of alpha is less than beta, then this happens if and only if minus beta, alpha lies between minus beta to beta. Okay, alpha lies between minus beta beta. Okay, so this is if and only. So now I have this one. So I can write reverse by taking absolute value of. So we have this one. Okay. So always remember this. Okay. So now move to next result. So we are going to prove a lemma. Okay. Let f close interval a b to r be a bounded function. Okay. Then supremum of fx1 fx minus fy is all such that x y belongs to closed interval a b is nothing but capital M minus small m, where capital M is supremum of f on closed interval a b and m is infimum of f closed on over closed interval a b. Okay, so let's prove it. So proof. Okay. So we have this relation. M is less than fx, comma fy. Both quantity are greater than equal to small m and less than capital M for all x, y belongs to closed interval a b. So their difference, because we know that small m is here, capital M is here, and in between fx and fy are lying. So their difference fx minus fy will be less than capital M minus my. Okay. Now changing x and y, nothing will affect. Either you take f minus fy or fy minus f. So we get fy minus fx, same thing, because you are taking different. Maybe it will be positive, non-negative, or if we take interchange, it will be negative. But this is always non-negative. Supremum minus infimum is always non-negative. Okay. So we have, so from what does it mean? It means I can take, so I can take minus common. So this is fx minus fy. Okay, that is m minus f. So let's say it's 1 and it is 2. So what we have? We have from 1 and 2, we have plus minus fx minus fy. Okay, always less than capital M. Okay. So I already told that, remember this. Alpha is less than beta means it can only minus beta, alpha, beta. But what is actually this? This is nothing but saying that plus minus alpha is less than beta. Because this is nothing but this. Okay. So same thing is happening here. So what does it mean? It means that fx minus fy is less than, because meaning of this is this, m minus m. Okay, meaning is this. So let's say it equation number 3. Not say equation number 3. So this is true. This is true for all x, y belongs to closed interval AB. So this implies supremum of fx minus fy such that x, y belongs to closed interval AB. This is capital M minus small m. This is 3, equation number 3. Okay. This is equation number 3. Okay. Now, since M is, what is M? Supremum of fx, x belongs to closed interval AB. And what is small f? Is minimum of fx such that x belongs to closed interval AB. Okay. So whenever you have a supremum, there is always a sequence such that sequence will converge to this. Okay. Similarly for infimum, so there exists, this implies there exists xn and yn sequences in closed interval AB such that fxn converges to capital M and small, sorry, fyn converges to small y m. Okay. Now fxn minus fyn is less than supremum fx minus fy such that xy belongs to closed interval AB. Because x and y are members of closed interval AB, and this is true for all n belongs to n. Now letting, and this is fixed quantity. So letting n tending to infinity, we get what we get. Letting n tending to infinity, what will be happen? What will happen? So this will be, we get, where this will tends to capital M, and this will tend to small m. Okay, so this is less than supremum fx minus fy such that xy belongs to closed interval a. Okay. but what we have, note that small capital M minus M is non-negative. Okay, because small m is always less than equal to capital M. So this implies m minus m greater than equal to 0. This implies absolute value of m minus m is nothing but m minus m. This. So what does it mean? What is this? What is this? This is nothing but m minus m. Okay. Okay. So let's say this equation number 4. From 3 and 4, what we have? From 3 and 4, we have capital M minus M is less than equal to supremum fx minus fy such that xy belongs to closed interval AB. This is by equation 4. And by equation 3, we have this one. So what we have actually? Now this is a quantity which is less than capital M minus 1 and greater than same quantity capital M minus 1. What does it mean? It means that both are equal. Xy belongs to closed interval AB. Okay. Capital M minus small m. Okay. So this is proved now. Okay. This is proved now. We will use this result. Okay. To show that if f is Riemann integral, the absolute f function is also Riemann integral. We will show by this result. Okay. So this result is done. Now move to next result. So theorem. So this is theorem. Let f closed interval AB to R be a bounded function if f belongs to RAB, it means F is Riemann integrable. Then mod F is also Riemann integrable over AB, and the integral of A to B fx dx dx is always less than integral of A to B mod f x dx function. Okay, so let's prove it. So note that fx mod value minus fy mod value is always less than mod of fx minus fy. This happens. This is an inequality. This inequality holds for all x and y belongs to closed interval. Okay. This happens always. Okay. Now let P be. Now first of all we have to show that f is Riemann integral. So for that first we have to show that mod f is bounded. Okay. Given that f closed interval a b to r is bounded. Okay. So this implies there exists small k greater than 0 such that fx for all x belongs to closed interval a b. But this is non-negative value. You take absolute value here, then it will not affect anything. So this implies. What this implies? Mod f is bounded on closed interval a b. Now let p is equal to a x naught, a is equal to x naught, x1, x2, xn is equal to b, be a partition of closed interval a b. We have f xi fx is equal to minus fy less than fx minus fy for all xy belongs to xi minus 1 to xi. Okay. Xi minus 1 to xi. Okay. So, but this cannot be exceeded by mi minus mi minus 1. Okay. So this happens. So if so, let m I dash is equal to supremum of fx x belongs to xi minus 1 to xi. Okay. And small mi dash is equal to supremum, sorry, infimum fx x belongs to xi minus 1 to xi. Okay. So what we have, let's say it equation number 4, 5, sorry. From 5, we have so from 5 what we have fx minus fy is less than fx minus fy for all xy belongs to xi minus 1 to xi. Okay. But this is less than supremum of fx minus fy subject xy belongs to closed interval xi minus 1 to xi. Okay. But what is this then? What is this then? This is capital Mi minus small mi. Okay. So what we have? We got we got fx minus fy is less than small capital Mi minus small mi for all xy belongs to closed interval xi minus 1 to xi. Okay. Now this quantity is fixed. Now this quantity is fixed. Fixed. This is fixed. So this implies supremum of f x minus fy xy belongs to closed interval xi minus 1 to xi is less than equal to mi minus mi. Okay. But so what is this? What is this? This is by lemma. What is this? By lemma, what is this? This is nothing but mi double dash, sorry, mi dash mi dash minus small mi dash. Okay. This is 4 I goes to 1, 2 up to n. Okay. So multiplying both the sides by delta xi, we get what we will get. So this implies mi dash delta xi minus mi delta xi dash capital Mi delta xi minus small mi delta xi. Now taking sum. So this is for I goes to 1 to n. Now taking summation over I goes to 1 to n. Then what we'll get? I goes to 1 to n. Mi delta xi delta xi mi delta xi. Now what is this? What is this? This is nothing but so UPF of mod f function. And what is this? LPF of mod f. What is this? UPF. This is, and what is this? This is LPF. So this implies this. Okay. So let's say this. Now, so we know that because this is always non-negative, this quantity is always non-negative. So we have this one, UPF LP. This is less than UPF LPF. Okay. Let's say this equation number 6. Since f belongs to RAB, it means f is Riemann integrable. We get limit non-p tending to 0 UPF minus LPF is tending to 0. Okay. So let's say equation 7. From 6 and 7, what we have? From 6 and 7, we get this is that limit non-p tending to 0 UP mod f minus LP mod f less than equal to limit non-p tending to 0 UPF minus LPF. Okay. But this is 0. But this is 0. So put this 0 here. This is less than limit non-p tending to 0 UP mod f minus LP mod f. Okay. Now tell me what is this? By sandwich theorem, this will be equal to 0. by Sandwich theorem. We have limit log p tending to 0 to p mod f minus lp mod f. This is 0. So what does it mean? When norm tending to 0 is UPF minus LPF difference is tending to 0, it is implied that function is Riemann integral. It means this function is Riemann, absolute f function is Riemann integral. So this is done. Now we have to show inequality. We have to take care of this one. We have to show this one. This one. A to B fx dx absolute value is less than A to B fx So first of all, what is this? Mod f means what? This is mod f means for all x belongs to closed interval. The meaning of this is this. So we know that this happens. So we know that this happens. So we know that absolute f x means absolute fx for all x belongs to x. Okay. So remember that, note that fx plus minus fx is always non-negative for all x belongs to closed interval a b. Okay. So what does it mean? What is this? This is nothing but the meaning of this is plus minus fx. Now this function is for all x to closed interval a b. Now this function is non-negative. So this implies this function. So what is this function? Mod f and f function are Riemann integrable. Okay. So by lecture, by Riemann integration, lecture 11, by Riemann integration, lecture 11, we have A to B mod fx plus minus fx dx is non-negative. Okay. Then how we can write this? This is nothing but This integral is nothing but, what is this? This function is nothing but a to b mod f x dx plus minus a to b fx dx greater than equal to 0. Okay. So what does it mean? It means a to b fx dx greater than equal to plus minus a to b fx dx. Okay. Now we have this one, so I can write in this way: a to b fx dx plus minus a to b f to dx. Okay. Now this is my alpha, this is my beta, and we have plus minus of alpha less than equal to beta, by which the inequality I have told in remember. Okay. So by this, what we have, I am using here this one, remember this. If alpha less than beta, if and only if beta alpha in this range, and this is happen when plus minus alpha is less than beta. Okay. This is also, this is equal to this. This is an if and only if. So what does it mean? It means mod of a to b fx dx is less than equal to a to b mod fx dx. Okay. Mod f dx. So this is done. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Thank you very much for today's lecture. Like, share, comment, and subscribe my YouTube channel. We will see you in next lecture. Thank you very much.